Yeah, so the last talk is going to be, so remember there were 3 talks and I said, there's 4 talks and I said in 3 of the 4, all the moduli spaces are going to be non-compact. So the last lecture was the one and only case where moduli spaces were compact. We're going to go back to a situation where all the moduli spaces are non-compact now. So I want to talk about P1 vortices. So this is vortices where the target space is P1, i.e. a 2-sphere. Okay, so this is a model that was originally written down in 1995 by Bench. Okay, so what's the setup? Well, we have a 2-sphere valued field. And let's, to start off, we'll just work on the plane. Okay, so physical space is just going to be a 2-dimensional plane, which we think of as being the unit sphere in R3. And what we do is we choose a unit vector in R3. So for example, 0, 0, 1 is an obvious choice, like E. And we're going to gauge rotations about that axis. Okay, so we introduce a gauge field. So let me call this sigma. And at some point, sigma might become a compact Riemann surface, in which case I should really formulate things using principal circle bundles and so on. But actually, even in the case where sigma is compact, all the situations I consider in detail, the underlying principal circle bundle will be trivial. So actually, you really can think of phi as being a function. Okay, so we have a gauge field, a 1 form on sigma, and we construct a gauge covariant derivative where we're gauging this rotation action. Okay, well, that's just the usual vector products in R3. And what we want to do is we want to run down an energy functional for things like this, so gauged maps to the 2-sphere, which has a Bogomolny story, which has a topological low energy bound saturated by a pair of first-order equations, which look like vortex equations and so on. So, what kind of theory should we write down in order to get that whole story working? Well, we know that the potential. So we're going to start off in the obvious way. So our energy is going to be an integral over sigma of gauge covariant gradients of phi squared plus curvature of our connection squared. And then we're going to add a potential. And what potential should we choose? Well, we know that what makes this thing work is if we take the potential to be half the square of the moment map generating the gauge action, right? So what's the moment map which generates this rotation, this group of rotations, the circle action on the 2-sphere? The answer is a height function. Okay, so if we just associate to each point on the 2-sphere its height above the equator, then the symplectic gradient of that function with respect to the usual area form, where we take the symplectic form to be the area form on the 2-sphere, precisely generates these rotations. Okay, so that's what we're going to do. We're going to take half the moment map generating the gauge action squared. Okay, so that's our energy. As I said, this was first written down in 1995 by Bernd Schroers, and he discovered the Bogomolny argument. So once again, just like I did in the second lecture, I want to think about what it means if we insist that our field has finite energy. So our pair consisting of a section and a connection have finite energy. Well, in order for this part of the integral to converge, we need phi to localize to the equator as we go off to the boundary of infinity in S1, in R2. So phi has to define a map from the circle at infinity to the equator side S2. Okay, but of course that can have non-trivial winding. Let's call the winding number n. Once again, finite energy requires that this term here goes to 0. And once again, exactly the same argument I went through in lecture 2 for the usual abelian Higgs model. It follows from that the total magnetic flux, okay, you can reinsert, you can use Stokes' theorem to rewrite that as the integral of A around the boundary, the circle at infinity, and then use this fact here, the fact that this quantity is vanishing on the boundary of infinity, to deduce that that's actually 2 pi n. Okay, so we have quantized magnetic flux, just as we did in the abelian Higgs model. Okay, but it turns out that there's another topological charge in this system because our target space is a 2-sphere, and we already have a homotopy invariant for maps from planes to 2 spheres, right? Namely the degree. So there's a related extra topological charge here. So what's the best way of thinking of that? So here the bundle picture really is quite useful, actually. So if we think about the total space, so if I was a section of a bundle, in the case I'm talking about, it's a trivial bundle. It's just globally sigma across S2. If sigma is compact, there are cases where, of course, it's non-trivial. But anyway, let's think about the total space of that bundle. So in the case I'm thinking about, it's just a Cartesian product. That has 2 distinguished canonical sections, namely the North Pole section and the South Pole section. So that point there and that point there are fixed points of the gauge action, right? So the section which maps every point in sigma to the North Pole, that's a well-defined section independent of gauge. Okay, so we have inside this total space of this bundle the North Pole section, and we also have the South Pole section. Now, we can always interpret, we can always associate to a section of this bundle its image, right, in the total space. So if you think, we can think of phi of sigma as being a submanifold of the total space of the bundle. Okay, so here it is, and we know that it's localized away from these 2 sections at infinity because of this fact here, right? Because it goes to the equator. So we've got some. That's supposed to be schematically writing. Okay, so this is a 2-dimensional manifold sitting inside this 4-dimensional manifold. These are also 2-dimensional manifolds sitting inside this 4-dimensional manifold. And there are 2 intersection numbers. There's the intersection number of this manifold with this manifold, and the intersection of this manifold with this manifold. So we can define 2 intersection numbers. The intersection of the image of the section with the North Pole section, and the intersection of the image of the section with the South Pole section. And they again are topological invariants because intersection numbers are topological invariants. But they're not independent of one another once we've fixed n. So if you think about it, if you wind around the equator n times, then the difference between the number of times you intersect the North Pole and the number of times you intersect the South Pole has to be n. The constraint n equals k plus minus k minus, yes, that's right. Okay, so the point is, if you just imagine this map from a plane to the 2-sphere, what it's doing is it's taking the boundary at infinity and it's wrapping it n times around there, and then you ask yourself, well, how do I fill in the middle? You could fill it up in the North Pole in the upper hemisphere, in which case you're going to hit that. You're going to have to hit that point n times with positive multiplicity. But you could also fill it in the South Pole, in which case you're going to hit that point n times with negative. Or you could do a mixture of the 2. So that's why you have this condition. Okay, so what we're seeing here is that there are 2 different kinds of vortex here. So if k plus k minus is 1, 0, then that's what I would call a north vortex. It has total magnetic flux 2 pi. And what it does is it just maps the whole plane to the upper hemisphere, where you wind once around the equator. Okay. But there's also something where you instead map the whole plane to the southern hemisphere. And if you're winding in positively around the equator, that means actually, if you intersect the South Pole with positive orientation, that actually means you're winding the opposite way around this equator. So that's a south anti-vortex, whose magnetic flux is minus 2 pi. Okay, so a south vortex would have this winding, this intersection number being minus. Okay, so there's two types of vortex and two different types of anti-vortex in this system. And in the usual plain vanilla abelian Higgs model, where the target is just a complex line, you have vortices and anti-vortices, but there's only one species. You can't have vortices and anti-vortices in stable equilibrium. If you start off with a configuration with a vortex and anti-vortex, they will attract towards one another and annihilate. Okay? Here, on the other hand, it's possible to have north vortices and south anti-vortices in stable equilibrium. That's what we're going to see. Okay, so remember we specifically chose this model. We chose this potential here in the hope that we were going to get a generalization of the Bogomolny story. Well, we do indeed. There is indeed a Bogomolny bound. So in the grand tradition of Bogomolny bounds, this doesn't have anything to do with Bogomolny. It was discovered first by Bernd, but it's a special case of something much more general that's already been explained in other courses. So it turns out that the energy is bounded below by 2 pi times k plus k minus with equality. If and only if, well, you already know the answer to this if you've been paying attention to the other courses. If and only if the 0, 1 part of dA phi is 0. So phi is holomorphic with respect to the structure defined by the connection. And the curvature, let me call that B, magnetic field, is equal to the moment map. So I guess if I'm thinking of this as a 2 form, I should really say Hodge dual of that is equal to the moment map, which is just phi dot. Okay, so that's the first vortex equation. And that's the second vortex equation. Okay, so as I said, I'm primarily going to be interested in the case where my domain is a plane. You can formulate this whole thing on a compact Riemann surface as well, in which case you need to use the language of principal bundles, associated bundles, and so on. If sigma is compact, there is again a Bradlow constraint. Okay, and again, it's just obtained by integrating V2 over the surface. Okay, so when we do that, we get 2 pi times this winding number, the total magnetic flux, which remember is k plus minus k minus. And that apparently is equal to the integral of phi dot E. Well, this quantity, whatever it is, obviously lies in the interval from -1 to 1. Okay, so the biggest it could possibly be is the integral of 1, which is just the area of the surface, and the smallest it could be is minus the area of the surface. Okay, so again, we get a Bradlow type inequality. If solutions to this pair of equations exist, then we must obey this pair of inequalities. But note that it's a bound on the asymmetry. It's a bound on charge asymmetry. Okay, it's not a bound on the charges k plus k minus individually. It's possible that there exist solutions with k plus and k minus arbitrarily large. They're not allowed to be very different from one another. That's the constraint. So we can have loads and loads of north vortices, even on a compact space, provided we also have enough south anti-vortices to compensate. Okay, so there's some high-powered symplectic quotient stuff. Which you can apply in the case where your domain is compact to deduce what the moduli space of solutions of this pair of equations is, right? So as usual, we're interested in the space of those solutions modulo the action of the gauge group. And it turns out that just as for the standards for linear vortices, for vortices we target the complex line, gauge equivalence class of solutions of this pair of equations are uniquely specified by divisors. But now it's a pair of divisors. It's the divisor corresponding to the intersection points with E. In other words, it's the divisor consisting of the points on sigma which get mapped to E. And also the divisor consisting of the points which get mapped to minus. Okay? And of course, those two divisors have to be disjoint, right? It's not possible for a point to get mapped to both E and minus E. Okay? So, I mean, I have to say it's not immediately obvious from the symplectic quotient construction. You have to do quite a lot of work to end up at that picture, but nonetheless, it's true that the moduli space of charge K plus K minus vortices is diffeomorphic to the space of divisors, effective divisors of degree K plus, which is the K plus fold symmetric product, right? Okay, so it's the space of pairs of divisors of degrees K plus and K minus, except we have to remove the ones where the divisors have points in common. So we have to remove what I would call the fat diagonal. Okay, so this consists of pairs of divisors of degrees K plus and K minus, which have points in common. Okay? So not really. Well, it depends what you mean. As we will see, not metrically, we don't know. So that really is singular. Sorry? Yes? Yeah, okay, but if you, okay. So I remember the start of my course is L2 geometry of moduli space. So I'm going on this moduli space, which is non-compact. And yes, you're right, you can compactify it. On this moduli space, there is an L2 metric, and that's the main thing I'm going to show you. And it turns out that does not extend to the compactification. Okay, so yes, you can compactify, but you lose the metric structure when you do. Or it has a singular metric, is another way of saying it. Okay, and that's not obvious. In fact, that's the whole point of what we've been trying to do to figure that out. Okay, good. So the point to note, yeah, that's very good. So the point to note is that this is non-compact, even if sigma is compact. Okay, so as I said, the primary focus of my interest is in the case where sigma is the complex plane. So in that case, as far as I'm aware, this symplectic quotient thing is just formal. It's not a rigorous mathematical construction. Okay, so this theorem that gauge equivalence classes of solutions to this equation are in one-to-one correspondence with pairs of disjoint effective divisors. Somehow you need to prove that differently. Okay, that doesn't follow. That doesn't follow from high-powered stuff of the type that you've heard about in Nuno's and Oscar's courses. Okay, so I just want to discuss briefly how you can still prove that this is true by doing sort of direct analysis of PDEs. Okay, so I guess what I want to explain is a theorem due to Yang, which is also in the mid-1990s. I'm not quite sure when. So shortly after Schröder's first wrote down this problem. Okay, so let P and Q be effective divisors of degree K plus and K minus, where again, I'm thinking of them rather informally. They're just collections of K plus and K minus points, possibly with repeats, okay? Let K be effective divisors on C of degrees K plus and K minus. But I'm going to insist that they're disjoint. Okay? Then there exists a solution of V1, V2 with phi with phi hitting the north pole precisely on P and phi hitting the south pole precisely on Q. It's unique up to gauge. It's smooth and it's exponentially localized. So this is a very direct analog of Taubes' original existence theorem for linear vortices on the plane in the case of P1 vortices. Okay, so how do we prove that? So the idea of the proof is, well, you really just follow the same strategy as Taubes did. So we trade in this pair of coupled first order PDEs for a single second order elliptic PDE for a single quantity, a single function H. But the price of doing that is that we have to introduce delta functions on the right-hand side of our PDE. Okay, so what we do is we define this quantity here, the log of 1 minus c dot phi over 1 plus c dot phi. And we note that that equals minus infinity on the plus divisor and infinity on the minus divisor, right? So this is on the plane. Okay, so you've got one divisor P, you've got another divisor Q. Okay, and it's just saying that the solution decays exponentially fast as you go up to infinity. Yep. Okay. So we define this function H in this way. It's basically just the log of the modulus of a stereographic coordinate of the two-sphere. It's not mysterious why you define it that way. Then it turns out that just as Taubes could reformulate V1 and V2 in terms of a PDE for his H, something similar happens here. And the PDE looks like this. So analyst Laplacian of H equals 2 e to the H minus 1 over the e to the H plus 1. That's true everywhere away from these two divisors where H is singular, but then at the divisors you have to add delta function sources to account for the singularities due to this definition here. So you have a bunch of delta functions where X is in the positive divisor, and you have to subtract off a bunch of delta functions associated to points in the negative divisor. Okay? So let me call that equation Y for Yang. And let me recall that this is very similar to Taubes' equation, So CF Taubes' equation. That said, del squared H, where H was the logarithm of the modulus of phi squared, right? The complex value section, is e to the H minus 1 plus 4 pi times the sum of all over all points in some divisor of the delta function. Yeah? Okay, so remember Taubes' theorem. So we know that, let me call this one T, that T has a unique solution. Let's call it for any choice of divisor. Let me call that solution HD, so label it by the choice of divisor, which is smooth away from D and exponentially localized. So it has a unique solution. Of course, I'm applying a boundary condition here, right? H of infinity equals 0 in both cases. There's a unique solution with the right boundary behavior. Okay, so we start off, what we're going to do is we're going to use a method called Perron's method, which means we need to identify a super solution and a sub-solution, where the sub-solution is below the super solution, and then argue that that means there must be a solution trapped between them. Okay, so let's consider the following quantity, minus HP. Okay, so you remember I fixed a pair of disjoint divisors P and Q. Let me take the divisor P, solve Taubes' equation with that divisor, with D chosen to be that divisor, and then define W0 to be minus that. Oh, I should have said HD is negative. That's also very important. Okay, remember we showed that HD was negative. Okay, so this is definitely positive. Okay. All right, so what can we say about this? Well, what can we say about its Laplacian? So that's minus this quantity here, right? So that's 1 minus E to the minus W0 minus 4 pi. Okay, so because HP solves this for the divisor P, it follows immediately that the Laplacian of W0, sorry, is that expression there, right? Okay, well, remember W0 is positive, okay? So this number here is less than 1, so this thing here is positive. Therefore, it's certainly less than the same number multiplied by any number which is at least 1, okay? And the number which is at least 1 I'm going to multiply by is that one, okay? So this is certainly bigger than 1, right? Just by definition. So this quantity here is less than this. And then formally, this argument is a little bit formal. You can make it rigorous by okay. So that's less than that, and so it's less than this. Sorry, I've done this wrong. I've chosen the wrong divisor here. Sorry, I should have chosen this to be Q. Excuse me. Okay, so what I do is, remember, I've got a pair of divisors, one where I'm looking for a solution where I hit the south pole, I call that Q, one where I'm looking for a solution which hits the north pole. Okay, so let me look at Taubes' equation, solution to Taubes' equation, where I choose the divisor to be the south pole divisor. Excuse me. Okay, then I choose W0 to be minus that. Okay, so everything is the same as I just said. Okay, so this is less than this here, and therefore it's less than this where I add a whole bunch of delta functions as well. Okay, so the point is, and then I can rearrange this, right? So the point is that this is, if I write this equation as del squared h minus the left-hand side equals 0, this doesn't satisfy the equation, the thing equals 0. It satisfies thing on left-hand side is less than 0. Okay? So that's what's called a super solution. Okay, so now we're going to do a similar trick, but instead of using the south pole divisor, we're going to use the north pole divisor, and we're not going to introduce a minus sign. Okay, so now let me define something else, W infinity, to be the solution of Taubes' equation, but where I choose the divisor to be the north pole divisor. Okay. So, and remember, all solutions of Taub's equations are strictly negative. So again, we can think about the Laplacian of that function there, that by definition, since it satisfies Taub's equation, is it's just that, okay? But now, because W infinity is negative, right? The exponential is less than 1, so now this is a negative constant, okay? So if I take a negative constant and I multiply it by a number bigger than 1, I get something smaller than the thing I started off with, right? So this is definitely bigger than. I think we can agree, right? And the same is true if I subtract off a whole bunch of delta functions, because delta functions are morally positive. Okay? So this then is a subsolution. Of Yang's equation. Okay, so here's the situation. Maybe I'll draw it in one dimension lower. It gets the idea across. Okay, so this is a sort of schematic picture of my complex plane. I choose a bunch of points P, the North Pole divisor, and a bunch of points Q. And from that, I construct two functions, one of which is associated with the South Pole divisor and is strictly positive. So it blows up at those points, okay? And it's a super solution of the PDE I want to solve. And the other one has singularities at the North Pole divisor, and it's strictly negative. And it's a subsolution. Okay, well, it's a general property of this kind of PDE, which I'll explain why it's true in a second. But if you have this setup for this kind of PDE, where you have a super solution which is strictly bigger than a subsolution, then there exists a solution trapped between them somewhere. Okay, and of course, this solution will in fact have singularities at those points. Okay, so how do you know that? Well, you can prove it using, so for a classical linear PDE like the Laplace equation, it follows very quickly. For a nonlinear equation, you have to do a bit more work. But nonetheless, it's very, very standard routine stuff. Okay, so the claim is there exists a solution trapped between W infinity and W0. Okay, and I've called them W infinity and W0, a solution of Y, I should say. Okay, I've called them W0 and W infinity very deliberately. What we do is we set up an iteration scheme. So let's define this function. F of S is 2 times hyperbolic tangent of S divided by 2. And note that its derivative is strictly less than 1. Okay. Then the point is our PD is of the form Laplacian of H equals F of H plus some deltas minus some other deltas, right? So that is just 2 tangent of S over 2. Okay, so our iteration scheme is the following. We're going to choose C0 bigger than 1. Okay, and then we're going to define, we're going to take our first, we're going to start with W0, which, let me remind you, is minus the solution of Taub's equation where our divisor is the South Pole divisor. And then our next iterate, this is always going to be defined as follows. Now, why is that a smart move? Well, the point is, this is now a linear PDE, a linear inhomogeneous PDE for omega n for Wn plus 1, right? So once we know Wn, to get the next iterate, we're solving a linear PDE. There's loads of existence and regularity theory for such things. So this thing definitely exists, okay? So we know that given Wn, we can definitely construct Wn plus 1. Secondly, if this sequence of functions converges, then by the way I've constructed it, there's a good hope that it's going to converge to a solution of the equation, right? So you might be asking, why did I bother subtracting off these two terms here? Okay. Well, that's so that I can use the following argument. So the claim is the following. This sequence is actually monotonic. Okay. So the claim is that okay, so every time we do this, we get something which is smaller than we plugged in. Okay, so that follows very quickly from the maximum principle. So you can prove it by induction. So first of all, you have to check that it's true in this case, and that's an exercise in using the maximum principle. And then you have to show by induction that if it's true for n, then it's true for n plus 1, right? Okay. So let's assume that Wn is less than Wn minus 1, i.e. Wn minus 1 is negative. Okay. Then let's think about the image under the Laplacian of the next one along of those things. Okay, so just by taking this PDE and subtracting off the same PDE but then replaced by n minus 1, we get that del squared Wn plus 1 minus Wn is minus C0, right, is equal to f of Wn minus f of Wn minus 1. The delta function sources all just kill one another, minus C0 Wn minus 1. Okay, now by the mean value theorem, so I'm really throwing high powered stuff at you today. By the mean value theorem, this is equal to the derivative of f evaluated at some point Sn between Wn and Wn plus 1 times Wn minus 1. Our induction hypothesis is that this quantity here is negative. Okay, and this number here is less than 1. So this is certainly bigger than okay? But remember, this is negative, okay? So this number here, oh no, this is exactly what you really don't want to happen. Yes. This is negative, and I chose C0 to be bigger than 1. So this is also negative, so the product is positive. Yeah, that was a scary moment. Okay, so what have I just shown? I've just shown that provided Wn is less than Wn minus 1, then the difference between Wn plus 1 minus Wn satisfies this inequality here, okay? But then by the maximum principle, it follows that this has to be negative, okay? So now, let me just remind you why that's true. So the maximum principle implies that Wn plus 1 minus Wn must be negative. Why is that true? Well, assume it isn't. So because these things are decaying to infinity at 0, it follows that this quantity attains a positive max. At some point Z star in the plane. But then the inequality tells us that the Laplacian at that point is bigger than this large number, large positive number. And remember, we're assuming that this is a positive maximum, so this is bigger than 0, okay? So if this weren't true, then there'd be a point which we have a positive maximum, and yet the Laplacian at that point is positive, okay? And you think of this as being the trace of the Hessian of this function. At a maximum, the Hessian can only have negative eigenvalues, right? And therefore its trace must be negative, so this isn't, that's a contradiction. Okay, so by the maximum principle, it follows that this thing here is negative, and hence Wn plus 1 is less than Wn. And that implies this monotonicity property, and then the monotone convergence theorem tells you that this sequence of things converges to something. Okay, now, of course, as a separate step, you have to show that the thing it converges to actually solves the PDE, and it has the right smoothness properties, et cetera, et cetera. The exponential localization properties are built in from the start because we have these estimates here, and these things are exponentially localized. So that's easy. Okay, so Wn converges to something, like the monotone convergence theorem, and then you have to show that H solves Yang's equation. And you have to get smoothness. That involves some work, but it's standard. And the fact that you get exponential localization, well, that comes for free with the. It comes for free because you started off with this bound, with these bounds here. All right, good. So, by working in that fashion, Yang managed to prove that solutions are in one-to-one correspondence with choices of pairs of disjoint effective divisors. Okay. So, the upshot, mk plus k minus c equals, is still true. That this moduli space is the space of pairs of effective divisors, of disjoint effective divisors. Okay, so that was a lot of fun. Of course, all we have is existence of moduli space. What we'd like to do, of course, is study the L2 metric on this moduli space, which is defined in exactly the same way as the other L2 metrics that I've discussed previously. You restrict the kinetic energy of the Lorentzian extension of the field theory curves lying in the moduli space. Yep. Yes. So you, yeah, this. No, but it was there. It was there because it was there because of the Laplacian. That depends on. Star FA equals something. I mean, in the Taub's formulation, the delta functions also, of course, they're associated with the measure and so on. It's the same. It's all very analogous. Yeah. Yes. So at the moment, I'm talking about, yeah, C Euclidean, so S2 with its usual round. Well, we're at it. Yes, go ahead. Yeah. Yeah. No, I mean, I didn't show this stuff here, and I didn't show this either. And again, it's the maximum principle. So it's another argument using the maximum principle. Okay. Any others? Good. Right. Excellent questions. That's what we like. Okay. So what I'm supposed to be talking about really is not the moduli spaces, which people here understand extremely well. but rather the L2 metric on the moduli space, which is a bit more niche, I would say. So again, we have an L2 metric. Again, it's defined by restricting the kinetic energy of the Lorentzian extension of the field theory to the tangent bundle of the moduli space. Okay, and again, we have a localization formula for it. So this is due to me and Nuno. From 2018, I think. So in order to formulate it, it's nice to do the following. So given any point zj in either one of these two divisors, the North Pole divisor or the South Pole divisor, let's define an associated sign to be +1 if zj is in P and -1 if zj is in Q. Okay, and once again, the localization formula tells you that you can write down the Kähler form for the L2 metric purely in terms of data associated with the behavior of this function here, which I've unfortunately just rubbed off, in the neighborhood of the two divisors. Yeah? Okay, so how does this work? So near a point zj, some point in either one of those two divisors, let me expand h. So h is going to have a logarithmic singularity. It's either going to be log of z minus zj squared if zj is in P, or it's going to be minus that. So let me get rid of that irritating minus sign by just putting sj to the left. Okay, so I'm expanding either h or minus h, depending on which divisor my point is in. So then it looks like that, and then it has a smooth part, which I can always take. In fact, it's analytic. You can definitely expand it. Okay, so in this way, we can extract from this solution, if only we knew it. Of course, we don't. But if we did know it, we could extract these functions here. So these are complex functions of all of the vortex positions. Okay, so all the points in both P and Q. Okay, so having extracted those functions, which depend on all those positions, I can again construct a 1-0 form. And we call it B. So we sum over all points in both divisors like that. Okay. It's a local 1-0 form. Then the theorem is that the L2 Kähler form on the plane, and there's a version of this on compact space as well, which is, you could probably guess how it looks. Basically, you just get a copy of the conformal factor for the surface in here. Okay, so we have this lovely magic which happened for the linear model as well, that actually the metric and the Kähler form can be understood entirely in terms of the behavior of this Taubes-like function actually at the singularities where phi is E and minus E. Okay, we just subtract off the singular part, Taylor expand the smooth part, extract the linear coefficient, and those numbers determine the metric precisely. Okay, and that's one reason why I think it's worth going through the pain of thinking about these PDEs. Because of course you can construct these moduli spaces if sigma is compact as symplectic quotients. And of course the Kähler form is defined as by some quotient procedure. But then if you actually want to get your hands on it, if you want, so for example, these moduli spaces are all non-compact. If you want to answer basic questions like, is it complete? Is this moduli space geodesically complete? Well, to answer something like that, you have to understand the behavior of this close to the fat diagonal, close to the points where the divisors are starting to coalesce, right? And this formula allows you to do that if you work hard enough. Okay, so I'm really supposed to stop now, but I've had lots of questions, so okay, thank you. I will take the remaining 10 minutes. Okay, so let's just focus on one simple but very interesting case. Namely, where k plus equals k minus equals 1. So in this case, even if we're in a compact space, our underlying circle bundle is trivial, right? Because k plus equals k minus. So then the moduli space, what is that? Well, it's the space of pairs of disjoint effective 1 divisor of degree 1. In other words, it's just sigma cross sigma with the diagonal. Okay? And in that case, it's not hard to show by an argument similar to the one I did for the linear model last time, that B globalizes as a connection on the anti-canonical bundle of that space. Okay, so you can interpret B, although there's a local coordinate expression for it, it has a nice global interpretation. Okay, so let's focus just on the simplest, well, in some sense, the simplest case. Let's take our space to be the line. Then I can always parameterize pairs of disjoint points using their center of mass. And so that's just a complex number and their difference. Let me call that thing epsilon. So that's capital Z. And that's epsilon. And that, of course, because they're not allowed to coalesce, is in the puncture plane. So in this case, the moduli space is just C cross puncture plane. And symmetry arguments imply that the L2 metric must be of the form just Euclidean metric with the mass of 2 vortices for the center of mass, plus some function which only depends on the length of epsilon. Okay, so the metric has to look like that just on symmetry grounds. Okay? By the obvious action of the Euclidean group on this moduli space. So what we really need to do is we just need to extract this function here. Okay, well, the point is we can do that. We can do it numerically, and if we work hard enough, we can also do it analytically. We can establish facts about it. Okay, so let me tell you first about the numerics. So what does numerics tell us? So by numerics, what I mean is solving the Yang equation in this case. So in the case where I have a vortex at epsilon and an anti-vortex at minus. So by doing numerics, I mean literally solving that PD numerically. Okay, you might think that's difficult because of the delta functions. You just subtract off the Green's function, you regularize it, you get a nice smooth PD. It's really not hard at all. So if you do the numerics, you find that it leads you to conjecture that actually this quantity here, the conformal factor of the metric, so this you can think of as being a metric on the relative moduli space, right, in the space of relative positions. Okay. It looks like for small epsilon, it actually diverges like minus 8 pi log of epsilon. If that's true, and the numerics are extremely persuasive, okay, for reasons that I don't have time to explain, and then it would follow that rule. First of all, M11 of C is incomplete. It would tell you that the scalar curvature, the Gauss curvature of this surface, the space of centered vortex pairs, goes to infinity. Okay, so this is how you know that the compactification can't be isometric, okay? Because if it were, you wouldn't be able to have divergent scalar curvature. And okay, so that's what you get for, and you can actually get an isometric embedding from the numerics. And what the space of centered vortex anti-vortex pairs looks like is the following. So if you isometrically embed it in R3 as a surface of revolution, it looks something like that, a bit like a symbol. So the tangent line is becoming horizontal here, but in a way which gives it infinite curvature. Okay, and it's asymptotically flat. You can show that's actually rigorous. We know that that's true. From which it follows that if you integrate the Gauss curvature over this centered thing, you would get total Gauss curvature 0. Okay, so the Gauss curvature is positive near the center and negative further out. And if this conjecture is correct, the Gauss curvature is negative. Okay, so that's what numerics tells you on the plane. If you've got a problem you're interested on the plane, and you want to make rigorous progress, what can you do? Well, you can cheat and put it on a compact space, and then the analysis all becomes much easier. So that's what Nuno and I did. Or you can get a good PhD student and give him the problem on the plane, him or her. And that's what I did. So let me just finish off by telling you some rigorous results. So all these statements here are based on careful numerics. Okay? They're not theorems. Okay? Let me tell you what theorems we do now. Okay, so first of all, in the case where our domain is the round two-sphere, then we know that the space of vortex-anti-vortex pairs is incomplete. And we know it has finite volume, and we've computed that volume. It's 2 pi times the area of the surface squared. And that actually is that's a very satisfactory answer, because it's just, if you think of these things as being particles of mass, the rest energy, the static energy, they have mass 2 pi. This is basically the volume of the classical point particle configuration space of such a system. So this is a nice answer, okay? And we proved that. How do we prove it? Well, we proved it by considering solutions of this PDE, but on the two-sphere, regularized, which turns into a nice, smooth, elliptic PDE on a compact space, and then you can do lots of estimates. So we actually estimated, although we don't know what H is, we can understand its behavior close to plus or minus epsilon, the vortex position. Okay, so in that way, Nuno and I, so this is work of me and Nuno. On the other hand, if you give it to a talented PhD student, then it turns out he can prove other things. So actually, René Garcia Lara, who's a student of mine, who's actually watching, hello René, I hope you're enjoying it. So he generalized this statement about incompleteness to a general compact surface with any metric you like. Actually, even in the case where you shift the vacuum manifold, so where your moment map is E dot phi minus tau, some parameter. So he even considered the asymmetric case as well. So big generalization. Showed that these are incomplete. Even better, I think, is he also established it in the case where sigma is the Euclidean plane. Okay, so there the analysis is significantly harder. Okay, so that's due to work by Garcia Lara, his thesis. And he also considered the case where sigma is a flat 2 torus. Okay, so we already know it's incomplete by this stuff here, but he managed to prove something about its volume. And this is really quite surprising. Okay, so the volume, it starts off looking like what you'd expect. It's just the It's just the volume of the configuration space of a pair of particles of mass 2 pi moving on a surface of area, whatever that is. Okay, but then there's a correction. It turns out you have to add to that 16 pi cubed times the area of the surface. That is really surprising. Why is that really surprising? Well, remember our formula for omega? It was well, is it still up there? Maybe I don't have to write it again. Yeah, here we go. Yeah. And remember, I told you that in the case k plus equals k minus equals 1, this thing here, B, is a connection on the anti-canonical bundle. If k plus equals k minus equals 1, which is the situation we're dealing with. Okay, well, of course, the anti-canonical bundle of a torus is trivial. The anti-canonical bundle of this moduli space, torus cross torus with the diagonal removed, that's trivial. Okay, so what we know is that this is a connection on a trivial bundle, and we're computing the integral of its curvature over this space. You would expect that to be 0, right? And if the moduli space were compact, of course, it would be 0. It wouldn't give any contribution. And without that, you just get precisely the area of the product metric on the surface, right? So without that, you just get this term, okay? And B is a curvature, sorry, B is a connection on a trivial bundle, but it's precisely the fact that the space is non-compact, and therefore, when you do Stokes' theorem, you get a boundary term. So it's precisely the term you get by integrating B over the boundary of this due to this diagonal. That gives you a non-trivial contribution, and you get that, which I think is fantastic. Okay. So yeah, sorry, I overran a little bit, and I should stop right there. Thank you very much. Probably, yeah. I mean, to be honest, I'm not intimately familiar with the theory you're talking about, but I can believe it, yes, sure. Yeah. Yes. Yeah, I know, I'm sure what you're saying is correct. Yes. Yeah, so so Yang, yes. Yeah, so in the case where the domain is a plane, I went through this proof by Yang, right? Yeah, in the case of compact, Yang also, in collaboration with two Zibners, husband and wife team, maybe, gave an independent proof. Same basic strategy, reduced it to a Taubes type equation, regularized, and then used yeah, in the compact case, we're basically using the existence theorem of Zibner-Yang, which I'm sure is a special case. But the reason to maybe appeal to the Zibner-Yang one is, of course, it gives you direct analytic information about the Taubes function, which is precisely the thing which occurs in our localization. So even when you have a more high-powered and elegant way of understanding the moduli space, it's still sometimes useful to get into the nuts and bolts of the PDEs. Yes. 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 Yeah, that's something I didn't have any chance to. But you have another lecture. When are you speaking? Yeah, so there's this formal compactification where the modular space is compact in Kähler, and you can compute its volume using cohomological tricks like I explained last time. And then you can take a limit. So there's conjecturally, there's this limit where this family of metrics on a compact modular space converges to the metric we're interested in. And then just take the limit and the formula for the volume, and you get, in this specific case, you get exactly. Okay, so this, in a sense, is verifying a big conjecture, which I didn't. But it's in my joint paper, Nuno. I've only written 2 papers. It's arduous work writing a paper. You end up having 6-month arguments about questions of notation, which I lost all of them. It's okay. It's okay. I forgive you. Ah, yes. Yeah, the only argument I was allowed to spell connection with an X. That's right.